Okay, good morning. So today we're going to continue with our class. We will look at uh, shaping process, which is material removal process, right? So and that's called machining, right? So the shaping process that we're going to look at today is material removal process, which is commonly known as machining process, and sometimes it's referred to as subtractive manufacturing. Okay, the term subtractive manufacturing is quite a new term to to be coined because it is referred to this process as opposed to 3D printing, which is additive manufacturing. Okay, so today we're going to look at machining and also powder metallurgy and 3D printing as well. Okay, so let's have a quick overview of machining process. Okay, so the machining process has been around for like forever. It's an ancient technique. Um, Early machine tools are like chisels and abrasive stones and um, that were used to shape stone, shape metals, etc. In the Industrial Revolution era in the 18th century, we started to have mechanized tools like lathe, milling machines, but most of these machines were still like manually operated. And during the world wars, the wars drove innovation, right? So we started to have automatic machines, and and at the end of the Second World War, we started to have the numerical control machine. Okay, so and then it is developed further to become the CNC machine, right? The CNC machine is sort of like an automatic machine uh, that couple the machining tools with computer to control the machine too. So you can just program it in and then just leave it to do its job. So because of the CNC machine or computer numerical control machine, we start to get some automation and we start to get good precision because we don't have to rely on human, which come with human error. Um, but in those days, the CNC machine, the programming of the machine is not done by coding as we understand it today, right? It's still used. It's still used coding, but the coding is done by using punch card, right? So sometimes it's called G code. You have a strip of paper and you punch holes in the strip of paper to tell the machine what to do. And to a modern era in the 21st century, the CNC technology continued to advance, and we started to get like multiple axis CNC machine, CNC milling, etc. And in the last 10 years, we started to get 3D printing. And was actually 3D printing has been around for much longer than that, but in the last 10 years, you can see that the 3D printing has been more commercialized, and it became a lot cheaper. And now you can buy a CNC machine to put in. Well, I'm sorry, you can buy a 3D printing machine or 3D printer to use in your home. Up to the present day, which is called Industry 4.0, we start to get a smart machining system with IoT and AI to transform the manufacturing processes. Okay, so let's have a look at the advantages of machining compared to other manufacturing processes. The first advantage is the precision. Okay, so machining process can give you much better precision than say casting or any other uh, manufacturing processes. You can control the precision and tolerance of your workpiece very closely. It is very versatile, right? So it's got a lot of versatility because the machining process can be used with a wide range of materials, including metals, plastics, ceramics, composites. Uh, so making it very very versatile. The surface finish, the machining can produce smooth and fine surface finish, right? So um, not only smooth and um, fine surface finish is good aesthetically. I mean, not only it looks good, it also reduces friction, right? Which is quite important as well. And the next advantage is customization. So machining can allow you to produce customized part quite easily. You can produce a prototype quite easily using machining process. You can produce low volume production. Uh, you can use it for low volume production runs. So it is quite adaptable. So you can change your design in the CAD program, and then you just put your design um, in the CNC milling machine, and it will just like mill out a new piece, right? So it is very customizable. So you don't have to make like molds before you have to cast it or something like that. So it is very customizable. It is very good for low volume production, right? But at the same time, we have a lot of disadvantages. Like we have a lot of material waste. Okay, so because machining is a subtractive process. That means you start off with a big lump of metals, and then you just cut out all the pieces, all the bits that you don't want, until you are left with the component that you want. So you have a lot of waste. Uh, so it is inefficient in that case, in terms of material cost, and also in terms of like um, the processing itself, right? It uses a lot of energy, right, in the machining process. Uh, for example, high-speed milling, when you're using a milling machine, it can consume a lot of energy, so it contributes to a higher operating cost. Okay, so um, and the machine itself is quite expensive, so you have a costly setup. So expensive machine together with the high waste, etc. So that makes the component, the workpiece that you get from the machining process quite expensive, right? So even though it is customizable, it is quite expensive to make. So it is usually used for prototyping or some one-off customization. That cost is the uh, secondary factor. It's not the main factor. Not like mass manufacturing. Um, Machining process usually limited to simple geometries. Um, some like complex geometries, complex shapes are quite challenging to be machined. So you have a limited in design possibilities, right? So it doesn't mean that it is not possible to machine a complex shape, but you need a more complex machine, which means more expensive machine. And um, more expensive machine or more money have well you sometimes you don't have to buy the machine itself. There are some shops that can rent out the machine, that you can buy the time for the machine, or you can order the machine to be made. But it makes it really like expensive for the time on the machine, and the machine itself. And The process can be quite noisy and there's a lot of vibration, right? A lot of the machining operation produce a lot of noise and vibration, which can make the workplace quite hazardous and might require additional safety measures, right? You have to use PPEs and also like some other additional safety measures. And also because of the high waste, there's an impact on the environment. Okay, so how are you going to get rid of the chips from the process? How are you going to get rid of the coolant used in the process? Because now the coolant is not clean, right? There's some like bits of metals in there as well. So you can reuse the coolant for a certain amount of time until it collects all the junk in there, so that it is not possible to be used anymore. So how are you going to get rid of it? Right? So you have to, it has to be managed quite properly. So that adds to the cost of the machining process. So in summary, there's a lot of advantages: precision, versatility, surface finish, etc. But a lot of disadvantages like waste and cost, etc. Right? Limited in the design. Okay, so the machining process involves usually cutting action, right? Cutting action, which is actually it is a shear deformation process of the work material, right, to form a ship, and then the ship is removed, creating a new surface. Okay, so um, we have a the cutting tool can be divided into two types. We have positive rake and negative rake, right? So the rake the rake refer to this angle here of the cutting edge, right? So this is the rake face. So this is a positive rake, right? So imagine the surface of the workpiece and you draw a line perpendicular to the surface. So this is a positive rake angle, and when you draw a line here, you have a negative rake angle. So there are some advantages and disadvantages of positive rake and negative rake, but we're not going to go into too detail on that. But anyway, so it is both of these type of tools perform the same function, which is this shear deformation on the surface. So basically, you move the tool on the surface, you apply shear stress on the surface, and the material start to be deformed, and then it will ship off. Right, so you have a ship, which is the piece of the excess material that you want it to remove from the surface, producing a new surface, which is going to be your workpiece. Okay, and machining is generally performed after other manufacturing process, such as casting or bulk deformation. Right, so um, if you remember when we were talking about casting and bulk deformation, like forging, sometimes you don't get the net shape, right? Some casting process give you near net shape, like investment casting, right? Some casting process give you a rough shape of the thing that you want to produce, and then you have to use the machining process to finish it into the shape that you want, right? So a lot of other manufacturing processes like forging, casting, need machining to finish the workpiece. Like maybe just a simple uh, hole has to be drilled, or sometimes you have to remove just a little bit of the surface to produce a smoother surface. For example, if you cast using a sand casting process, the surface might not be smooth, the tolerance might not be good enough. Then you might use machining process to smooth the surface, and make the tolerance acceptable. Okay, so other processes create general shape of the starting work part. Like I just mentioned, you use casting to generate or produce a general shape of the product that you want, and then the machining process provide the final shape, final dimension, the final finish, and special like geometric detail that the other process cannot give you, right? So okay, so um, for a machining process, a sharp cutting tool is used to cut away material to leave the desired part shape, right? So you start off with a general shape from other casting process, from other manufacturing process like casting, and then you use the cutting tool to cut away the material, the excess material, until you get to the shape that you want. Uh, And like I mentioned earlier, the cutting action involves shear deformation of the workpiece to form a ship. Okay, so the important parameters in machining is uh, the important parameters are the factors that you have to consider when you are using machining process. You have to optimize these parameters so that you can get a good high quality product. You can and the process will be more efficient, right? The first parameter that you have to consider is the cutting speed. Okay, cutting speed is uh, the movement of the workpiece relative to the tool, right? Or the tool movement relative to the workpiece. Okay. The next parameter is the feed rate. The feed the feed rate is the rate of tool advancement into the workpiece. So these two can be quite confusing, right? So the cutting speed is how, for example, for a lathe, the cutting speed is how fast your workpiece is spinning, and the feed rate is how fast is your cutting tool moving into the workpiece, right? And that depends on the depth of cuts or the thickness of the material removed in one pass. Tool geometry like rake angle, clearance angle, cutting edge radius, etc. Right. So these are really important parameters. Like you can see all these different cutting tool geometries. You have different um, nose nose radius, nose angle, edge relief, like etc. Right? The amount and the type of coolant or lubricant used to reduce heat and friction that is that is something to be considered as well, because uh, a, a good coolant for one type of metal might not be good for another type of metal. Like it might be corrosive to another type of metal, for example. Um, Tool material, right? You have a choice of tool material like high speed steel or HSS, carbide or ceramic tools, right? So HSS is a type of tool steel that we've learned about just a little bit in just before the midterm when we talked about ferrous alloy, right? A type of ferrous alloy with a lot of alloying additions is called a tool steel. So tool steel is a type of a group of alloys that are used to make tools like cutting tools, molds or dies or punch, etc. Tool speed, the like spindle rotation speed, how fast the tool can move, can spin. Tool engagement, like portion of the tool in contact with the workpiece. Tool wear monitoring, right? So you have to monitor uh, how much of the tool is worn down, so that you have to change the new cutting bit, because because if you don't have a good and sharp tool, you will not produce a good and smooth surface. Okay, uh, so for a machining process, there are three important parameters. We call it three dimensions of machining processes. Right, so we have cutting speeds, feed, and depth of cut. Right, so cutting speed V is the primary motion of the process. The feed is the secondary motion, and depth of cut is the penetration of the tool below the original work surface. For certain operations like turning, when you're operating a lathe, the material removal rates is uh, VFD, right? So it's the material removal rate depends on what is your cutting speed, what is your feed rate, and what is your depth of cut, right? So basically, when you're turning up the workpiece and you are moving the cutting tool onto the workpiece, how fast are you turning the workpiece? How fast are you moving the cutting tool? And that will give you how much material removal, right? So basically, it's just the volume of the material removed in a uh, certain time, right? Okay, because cutting speed is what? It's just like um, meter per second, right? So this dimension and over time, feed is also dimension uh, and depth. It's also dimensions. So you get like three dimensions. So you get a volume, right? Over time, which is the rate of material removal. Okay, um, machining process can be divided into conventional machining process, uh, abrasive process, and non-traditional machining. Right. So in this course, we're going to concentrate on conventional machining process. So the machines that you can find in any like workshop, right? Um, for abrasive process, they're usually used to produce a smoother, better surface finish, like grinding, etc. So we're not going to go into detail on that. And non-traditional processes like um, that are not typically mechanical process, like electrochemical machining, like EDM machine, electro discharge machining. So you have, or we sometimes we use the term wire cutting, like colloquially. So basically, we use electricity and uh, electrochemical process to actually cutting a piece of metal by applying current to two pieces of metal, and one will be sort of like dissolved by the process. So it's not traditional. So for the traditional or conventional machining process, they are mostly mechanical process, and you can find these machine tools in nearly all like mechanical workshops. The first process is called turning and related operation. The second is drilling and drilling related operation, and also milling, right? So these are the three most important machining operations, like turning, drilling, and milling. Okay, and you have other machining operations like shaping and planing, broaching, and sawing, right? So turning is basically uh, when you are using a lathe. So basically, you are turning your workpiece and moving the cutting tool in there, and like to cut away the excess material. Drilling is just basically just making a new hole in a piece of the material, right? And milling is cutting, producing a new surface, like usually like three-dimensional surface. So you can have okay. So the main difference between turning and milling is that for turning, the workpiece is rotated, and the workpiece like sort of stay relatively still, right? But for milling, the workpiece stay relatively still, and the tool is rotated, right? So those are the main disadvantage, the main differences between turning and milling. And the difference between drilling and milling is that even though they are quite similar in a way that the tool is actually rotated, right? For drilling, the tool is rotated. For milling, the tool is also rotated, but the movement of the tools are different. For drilling, the tools is rotated, and the movement of the tool is just going up and down, like to produce a hole. But for milling, the tool is rotated, and then can move in three axes, X, Y, and Z, right, to produce like three-dimensional shape. Okay, so next we'll look at the cutting tool, right? So cutting tool classification. The cutting tools can be divided into two types. We have single point tools and multiple cutting edge tools. So single point tools, basically you have one dominant cutting edge. The point is usually rounded to form a nose radius. So it looks something like this. You have this cutting tool here. You have a nose radius here, and you're actually using this nose to cut into the piece of material. You're not using the whole face of the cutting tool, right? You're using just this bit here. And single point tools are used in the turning process mainly. Okay, so basically you're turning your workpiece and use the cutting tool. Use the single point cutting tool to cut away on the surface. For multiple cutting edge tools, we are usually using these cutting tools for milling process and drilling process. Right? Usually, the multiple cutting edge tools, well, you have more than one cutting edge. The tools are rotated, right? So the motion relative to the workpiece is achieved by rotating. Okay, so for single point cutting tool, the tool doesn't rotate, but the workpiece rotates. But for multiple cutting edge tools, the workpiece doesn't rotate, but the tool itself rotates. Okay, so um, because it has multiple cutting edge, so if the tool doesn't rotate, then you are just using just one cutting edge, right? So that's why for the multiple cutting edge tools, the tool has to be rotating, so it can sort of like alternate between different cutting edges. And these are used in drilling and milling processes. Okay, next we'll look at the classification of machine parts. So the machine parts can be classified in terms of the geometry, right? So the first one is called rotational machine parts. Okay, so rotational machine parts, so the part actually rotates, and because of the rotation of the machine parts, you can produce cylindrical or this shape workpiece, right? So the cylindrical workpiece, it doesn't have to be circular in cross section. It can be ellipses as well, right? So you can do turning, but you can do off-centered turning to produce like more ellipsoid shape product. Okay, so that's for rotational, right? So, but the main difference between these two is that for rotational workpiece, you can see that it is sort of disc-like shape, cylindrical shape, more circular, more rounded, right? But for non-rotational, you get block-like or plate-like product. Okay, so um, you get for different type of parts, you must use different manufacturing process, right? So if you want a more cylindrical shaped product, you will use turning using a lathe. But for like block shape or non-rotational, you would use something like a milling machine or drilling machine, right? Or mostly milling machine. Um, um, each machining operation produces a characteristic part geometry due to two factors. The first one is the relative motion between the tool and the workpiece. Okay, and the second one is the shape of the cutting tools. Okay, so the relative motion um, gives you the like primary shape, right? So this is for a generating process. If the part geometry determined by feed trajectory of the cutting tool, right? So you are generating a new surface by cutting into the workpiece. But okay, for generating process, your cutting tool will not have any like fancy shape. You just have like either like one cutting edge or maybe cylindrical but multiple cutting edges. You, you are basically just generating a new surface. Okay, but for a forming process, the shape of the cutting tool will be like quite different, and the part is created by the shape of the cutting tool. Okay, so the first one for generating, the shape is created by the movement of the cutting tool. Okay, the second one shape the for forming process, the shape of the workpiece is generated by the shape of the cutting tool. Okay. Okay, so for generating processes or generating shape, you can see that you can use the same cutting tool, right? In this picture, and this picture, you're using the same cutting tool, but you're producing or generating different shapes by different movement of the cutting tools. Okay, so if you feed the cutting tool like linearly, like parallel to the workpiece, you're producing a cylindrical shape. And if you're moving it like diagonally, like this one, you are producing a conical shape. Or if you're moving it in this fashion, you get this like wavy surface, right? So this is this is called generating. Okay, so you have basically just like quite basic cutting tool, but you're moving it differently to get different surfaces, right? For the same goes for milling, right? So you can produce a new surface, or you can on top or on the side, depending on the movement of the cutting tool, right? But for forming, you can see that the cutting tools have different shape, have like odd shape, and the workpiece will have the same shape as the cutting tool, right? This is called a forming process, right? Like forming new surface in this case, and drilling and broaching. and you can have a combination of forming and generating as well. So in this case, you can see that um, the T-swap milling can produce a new surface just like generating, but because the shape of the milling bits produce a T shape, right? So the shape of the product is according to the shape of the cutting tool, just like in the forming process, right? So you can combine the forming and generating processes, or in like uh, a threading tools when you want to make a thread for a nut or bolt. You are you are using this threading process, right? So the shape of the thread is conform to the shape of the threading tool, but at the same time you're moving the cutting tool like in the generating process. Okay, the first machining process that we are going to look at is called turning. Okay, so a turning process uses a machine which is called a lathe. Right, so the machine is called a lathe, and this process produce a workpiece that is um, more or less cylindrical. Okay, so we are using a single cutting edge tool to remove excess material by rotating the workpiece, and then we are moving the cutting tool to produce the cylindrical shape that we want. Okay, so this machine is called a lathe. So, and we put the workpiece inside uh, the workpiece holder, and you can have different type of workpiece holder, right? You can have different holder, or um, or fixture, right? So it can be, well, and then different shape is called differently. So like for example, this one is called jaws or adjustable clamp, right? This is most appropriate for like cylindrical workpiece, when you want to produce a workpiece that is like sort of cylindrical with circular cross section. Okay, so basically you have different. Well, we have three jaws here, right? And uh, when you're turning the key to lock the workpiece, all these three jaws will move at the same time. So it will lock the workpiece in the center without having to try to center the workpiece. Okay. For longer workpiece, if you want to um, if you want to turn a longer workpiece, you might need a centering piece, right, to hold the workpiece in place, because when you have a longer workpiece, when you're turning it, it will sort of it will not just turn in place, right? It will just sort of like sway a little bit as well. So you need this sensor to push against the workpiece and hold it in the center. Okay, so uh, the in that case we're using a fixture which is called a dog plate, and also and um, in this case, when we have a face plate, you can see that there are four jaws in this case, and those four jaws move independently. So we can put our workpiece in off center, right? So we can put our workpiece in off center. So when it is turning, and when we are cutting, we'll cut on the surface, but not evenly in all the surface, right? So compared to these adjustable clamp, when we put our workpiece in here, and the jaws move at the same time and clamp our workpiece in the center. When we are cutting it, it will cut on the surface evenly throughout the surface, giving you a circular cross section. But in this case here, when you have four independent jaw, but when you can move jaw differently, so you can load the work part off center, right? So when you load the work parts off center, you will cut one side more than the other. You will end up with cylindrical shaped workpiece. I'm sorry, you get cylindrical shape, but the cross section is more elliptical, not circular, right? So because you are cutting on one face more than the other face, so one face is cut more, so it becomes flatter on that side, and the other face is less, so it like more rounded. So you get sort of like oval shape or elliptical shape workpiece. Okay, um, so there are a variety of generating and forming process performed on a lathe, right? So like facing, facing is basically you are just cutting the surface evenly throughout to produce a new surface. So you are getting a smaller diameter workpiece, or turning. So basically you are producing a taper surface, or contour turning. Like in this case here, you have a contour, right? And form turning. So this is a forming process, not generating surface, right? So you need a tool to form the surface. Uh, chamfering. Chamfering is when you are cutting. Well, for example, if you're cutting a piece and the edge is really sharp, right? You are using chamfering to remove the sharp edge of the workpiece. Cut off is when you want to cut your workpiece like to a certain length. You just move in this direction until your workpiece is cut into smaller piece. Okay. Threading is it's just basically making a thread on a bolt, for example. Boring is digging a hole, right? So you have a boring bits, right? So you're just like uh, boring, making a bore, and drilling is just like making a hole, right? So going back to the beginning of machining, one of the first machining machine that has been produced was produced was a boring machine, right? So it's a lathe used specifically for boring the barrel of a gun, right? So that was that was the driving force for the machining operation during Napoleonic War, I think about 200 years ago. They are trying to produce a better gun for the war. So they are trying to produce a better barrel for the gun, more durable, stronger barrel. So they are using this boring process to to produce the barrel of a gun. Um, Initially, the barrel of a gun, a long gun, was cast, and by casting process, now you know that casting process have a lot of defects. So the guns are not really durable. So after firing the shot, like a few hundred times, the gun might burst, right? Might explode because of a lot of the casting defect. So they think that if the casting process is not suitable or it's not good enough to produce a durable gun, then what other process can they do, right? The casting process was used because it was the easiest process to produce a cylindrical shape with hole inside. Next, they start to produce like a long rod, and then they are using the bulk forming process, like rolling, to produce a thin rod, a long rod, which is stronger because of the cold working. Right, cold working, you have work hardening, right? And then they start to cut a hole inside. Initially, using a similar to a drilling uh, a process, but because the for a long gun, the drill bits has to be long as well, and that is not very suitable because when the drill bit is long and when you are keep drilling like a deep hole with a drill bit, the drill bits get hot and it warp. So the hole inside is not like a straight hole, right? So they started producing this boring bits, right? So you have a single cutting edge here, and it start to as the workpiece turn, it will start to cut on one edge and then like going down and down and down and down to produce a ball, right? So that's a um, boring process. We use the same term boring for digging tunnel, right? So um, one of the companies of Elon Musk is called the Boring Company, right? Boring in this case refer to like digging tunnel, not 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 uh, um, it doesn't mean uninteresting. Right? Okay, so the next process is called is drilling. Drilling is uh, a technique that we use to produce a hole. Drilling is used to create a round hole, usually by means of a rotating tool with two cutting edges. Right, so you have the cutting edge tool is called drill bits. Right, so we have drill bits, and the drill bits usually have two cutting edge, like in spiral configuration. And the machine tool is called drill press. Okay, so the drill press can be like tabletop drill press, or can be like floor standing drill press. Okay. So basically, the drill press will have a base, the column, the head, and the adjustable head, and the spindle, which hold the drill bits, and the spindle will turn, right? And you have the table to adjust for the height of the workpiece, and you have this handle here to activate the drill, right? So you pull the handle, so the drill bits will come down and drill a hole. Or you can have like more like automatic machine to drill um, holes for you, like in this picture. Okay, so um, we have other operations that are related to drilling, right? So drilling is drilling is to produce a hole, right? But we have other operation which involves holes, but it's not just drilling a hole, right? Like for example, reaming. Reaming is a process to widen a hole. So you might drill an original hole and maybe it's like too narrow. So you are using a reaming bit to widen the hole, right? So uh, why do you want to widen a hole? Why do you want to widen a hole? Because you want a better tolerance, right? So in drilling, sometimes you get a small hole, and in drilling you get the tolerance for drilling is not as good as reaming. So if you want a hole with a tight tolerance, you might first drill a hole and then you use the reaming to get a good tolerance of the hole. and also you get better surface finish inside the hole by using a reamer. Okay, so the reamer looks pretty much very similar to the drill bit, but the main difference is that the flute on the reamer are sort of like straight through, not spiral like the drill bits, right? So the flutes on the drill bit, the drill bits are spiral, but the flutes on the reamer are sort of straight. Tapping process. Tapping process is a process when you want to produce internal thread, like for to accept a bolt or a screw, right? So you want internal thread, so you use a tapping tool, right? The tapping tool is called a tap. Okay. Next is counter boring. So basically, counter boring gives you a stepped hole, right? Basically, you drill a hole first, and then you are counter boring the top bit. So it's quite similar to reaming, but reaming you are enlarging the whole depth of the hole, right? But counter boring, you're just enlarging the opening of the hole. The reason why you want counter boring is that when you want your bolt, you don't want the head of the bolt to be protruding on the surface, right? So you want the head of the bolt to be flush on the surface. So you are counter boring so that the bolt will sit in here and flush with the surface. And you have right, so the bolt head will be like sort of in the hole. Okay. Um, um, Next is countersinking. Countersinking is similar to counterboring, uh, very similar to countersinking, counterboring, but instead of having a sort of like step hole like counterboring, now you have a uh, cone shape hole for so that you can put in like flathead screw and flathead bolts. Okay. Okay. So so when you have a flathead bolt like this or flathead screw like this, you do countersinking, right? So the screw will just go and sit in the hole quite tightly. But if you have a bolt that shapes something like this or something like this, and you want the bolt to sit flush on the surface, you do counter boring, and the head of the bolt will just like go into that enlarged hole, right? So basically, countersinking and counter boring serve the same purpose, but because of the shape of the bolts or the shape of the bolts or screws are different, so we use different tools to produce the appropriate hole, right, between the counter boring and counter sinking. Center drilling, center drilling or centering. Uh, Basically, this process is to drill a starting hole, right? To drill a starting hole to establish a good location for subsequent drilling, right? So basically, if you want the center of the hole to be a certain distance from a certain place, for example, if you want the center of two holes to be exactly 10 centimeters, you do the centering or center drilling for these holes first, because the center the The center of the hole is quite small for center drilling, so it is easier to measure a correct distance between the two holes, right? And then because you have the center of the hole marked by centering process, you can use a bigger drill bits to actually drill the hole, and you can be sure that the center is exactly the distance that you want because you do the centering and measure the distance to the center already. Um, okay, the next drilling process is called spot facing. It is very similar to milling because it is used to provide a flat machine surface on the work part, right? But the difference between spot facing and milling is that it is very localized. So, for example, if this area is sort of protruding on the surface, you use spot facing to get rid of that bumps on the surface, right? Because the workpiece doesn't move in the x and y axis, it just moves up and down. So it can get rid of that small bump in that local area. It doesn't move around. Okay, so that's the drilling process. Next, we will look at the uh, milling process. Okay, so uh, for the milling process, we are using multiple cutting edge tool, right? By rotating the multiple cutting edge tool and move it across the workpiece, we can cut away the excess material that we don't want, and then we can cut either like plain or straight surface on the workpiece. And there are two forms, essentially there are two forms of milling. The first one is called peripheral milling, and the second one is called face milling, right? The peripheral milling is by removing like the total face of the workpiece. So basically, you're moving like the like around the edge, for example. You are removing the periphery of the workpiece, right? When you're moving the milling cutter on the surface, you are producing new surface. And face milling, face milling is producing new face on the surface, right? Um, Typical peripheral milling includes slab milling, like in this picture here. This is called slab milling. When you're milling the whole surface, right? This is called slab milling. You can have slotting or slot milling. When you're milling a slot on the surface, you can have you can do the side milling. When you are milling on the side, it's still considered a peripheral milling because you are like milling around the face of the workpiece. Straddle milling because you are straddle the workpiece with two milling bits, right? And you are milling two sides. And also you can have form milling when the shape of the milling bits are different from like normal spiral shape, right? These are all peripheral milling. And for face milling, you can do slab milling in this case, or you can do um, slotting. I'm sorry. Um, okay, this is conventional face milling, partial face milling, right? Partial face milling because you are milling just like part of the face. End milling or profile milling, pocket milling, and surface contouring. Right, so you can do a lot of things with milling, right? But these groups of milling technique are divided into peripheral milling and face milling. Okay, so the difference between peripheral milling and face milling is that the Peripheral milling, you are like removing the outside, like the 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 top bits, right? So, okay, or you can think of it as the milling bit is sort of um, being all horizontal and removing the total the whole workpiece. But face milling, you are using like the open face of the workpiece, right? So the milling bits are vertical, right? So those are like two main different. You can think of it as the shape that is produced by milling different part of the workpiece, or you can think of it as the movement or the motion or direction of the milling tools, right? For peripheral milling, the milling tools are in this configuration. The rotation is uh, for horizontal, but for face milling, the rotation of the milling bits is in the vertical rotation. We have vertical rotation, right? So those are the two different milling technique. Okay, so uh, next we will look at other machining operations. So um, these machining operations are used to produce like um, some sort of um, difficult shape to be machined by other technique, and also to produce good tolerance and precision. Okay, so the technique that we're going to look at is shaping and planing, broaching, and sawing. Okay, so um, shaping and planing are similar operations. Both use a single point cutting tool, move linearly relative to the work part. Okay, so the shaping machine and the planing machine look very similar, and the the action is very similar as well. If you have a casual glance on these two pictures, they might look the same, right? But they're in fact quite different, right? If you look at the direction of the motion of the tools of the workpiece, you can see that they are different, but they are producing the same type of uh, workpiece, right? You're producing a straight flat surface in both of these operations. Okay, they are interrupted cutting operations, so they are not continuous, unlike uh, turning or milling. Uh, the the tool is subjected to impact loading when entering the workpiece. The, the typical tool for this operation are single point high speed steel tool. Right, so basically you are using like high speed steel as the cutting bits. Um, we have a low cutting speed because this due to the start stop motion of the cutting tool. Okay. 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 I forgot to mention a little bit about the cutting tool. I mentioned the high speed steel, right? But in fact, high speed steel is just one type of the cutting tool that we can use. We can use like carbide and ceramics, etc. cutting tools as well. Um, for for really hard material, sometimes the um, sometimes the cutting tools is not hard enough. So we have different type cutting tools. Okay, this is not in your slide, but um, okay. So for the cutting tools and the material for the cutting tool that we need good high strength and high toughness, but at the same time we need hardness and wear resistance, right? We, uh, we need high strength because usually high strength material have higher hardness as well. So if you want to cut something, you need to cut it with something that is harder, right? And you need high toughness so that it doesn't break easily. And also you need hardness and wear resistance because you want to use your cutting tool for a long time. And you can see that high-speed steel HSS had really good strength and really good toughness, but it doesn't have hardness or wear resistance. So high-speed steel can be worn down quite easily for using with harder material. So for harder material, we might use diamond-coated drill bits or diamond-coated milling bits, right, or cutting bits, or we can use like all these ceramic cutting bits or composite material like cements. We can use carbide, etc. But all these material here, they are quite brittle. So we are not producing it in the same way. We are not making the tool in the same way as the high-speed steel. For example, the high-speed steel bits, you might produce the whole cutting bit in this like in one piece. Right? So the whole piece, the whole of the cutting bit is produced using uh, high-speed steel because it's quite tough. It can withstand the vibration quite well. But for carbide bits or ceramic bits, it is quite brittle, so you don't want the whole piece to be made from ceramics or carbide or diamond. So we are using the tool holder, which is produced using high-speed steel, and we have an area for an insert, right? So we have the seat or the shim for the insert, which is made from other harder material like carbide, like tungsten carbide or cermet or silicon nitride or diamond coated bits, right? So this is a single point cutting edge, so we only need this bit to be hard, right? So all the other bits around here has to be like strong and has to be tough, etc. So we use high speed steel to produce the tool holder, and we use other material like ceramics and carbide, etc., to produce the cutting bits. Okay, so uh, the cutting bits for the shaping and planning process are usually made from high-speed steel because of the high impact. Okay, because the um, high-speed steel has good strength and good toughness. Okay, so when you apply an impact load to the high-speed steel, it's gonna absorb that impact energy. But if you're making the cutting tool with ceramics, when you are when you are applying the impact loading, the ceramic might explode or might break, right? So that's why for this type of machining, we're using uh, high-speed steel as the cutting tool. Okay, so the machine for the shaper and the planer, the machine for the shaping process and the planing process are called shaper and planer. They look similar, but the action are quite different, right? So for the shaping process, you can see that the the for the shaping process, the workpiece stay still, right? In this case, the workpiece stay still here, and the uh, the shaper will have a ram that moves the tool head back and forth, right? So when it moves back, it will move the workpiece like from left to right, or we call it the feed motion. So it starts from the right hand side of the workpiece, and it will move from right to left, right? So it will feed from I'm sorry, it will feed from left to right, not from right to left. Okay, so the head will move from back to front, cutting a new surface, and when the head move back, it will feed uh, the workpiece one step, and the head will move forward again, cutting the surface, and then move back. Okay, so you can see that it is a non-continuous cutting process, so it is quite slow because you have the start-stop process, cutting and then stop cutting and then cutting again. Okay, so this is a shaping process, but for a planing process, the planing process, the tool head stays still, right? The tool head stays still relatively because the workpiece is moving along this rail here, right, along the base. And after one movement, the tool head will be fed in one like motion, right? So the tool heads will be fed from right to left, cutting from this edge here, and then it will be fed just one more step and cut another step, right? So the two processes are very similar. The finished workpiece will look the same, but the movement of the workpiece and the cutting tool are different. They are in fact opposite to each other, right? So for the shaper, the workpiece stay relatively uh, still, and the two head move back and forth. For the planer, the workpiece move back and forth, and so those are the different. Next process is called broaching. Broaching is a multiple tooth uh, a multiple tooth cutting tool that is moved linearly relative to uh, workpiece in direction of two axes. The cutting tool is called a broach. So this is a broach, right? So this is the cutting tool, and you can see that there are a set of teeth on the broach, right? Like in this picture here. Okay, so the first one might eats into the surface just a little bit. Another set of tooth will go a bit deeper and then deeper and then deeper. So a broach, you have a set of teeth here, right? And when you're moving the broach through a workpiece, you produce like a bigger and bigger and bigger hole and the shape that you want. Okay, so the broach is moved like, imagine this broach on top of this workpiece here, right? So you're moving the broach down here, and it will produce this foam surface. You have an internal hole and a slot using a broach. Okay, so advantages of broaching is that you have good surface finish because the cutting bits will just cut the surface and leave you a smooth surface. You have good tolerance. You have a variety of work shape possible. So you can have either external broaching, like the area that is like sort of hashed, yeah, has been broached, right? So you have external broaching and also internal broaching, right? All these holes are broached, right? You have different shapes, different shape broaching tools. You can have different shapes of the broaching, right? So disadvantages is expensive tooling. Like the broaching tools, are quite expensive because you have complicated and custom shaped geometry of the broach. So that makes it quite expensive, and that is one main disadvantages of broaching. Okay, Sawing operation is um, an operation that cuts a narrow slit in the work by a tool consisting of a series of narrowly spaced teeth. The tool is called a saw blade, right? So you might be more familiar with this type of machining, right? So because you might have used a saw before. So anyway, so typical function of a sawing operation is to separate a work part into two pieces. Okay, so or you can use it to cut off unwanted portion of the part or cut outline of a flat part. Right? You can have power hacksaw that move back and forth and cut into the workpiece, right? Or you can have a band saw. In this case, it's a vertical band saw. So you have a band of um, narrowly spaced teeth, and it is moved or rotate around the two axes, and you can move your workpiece past the blade, right? And then you can cut your workpiece, or you can have a circular saw, right? So um, okay, so that's different type of machining. So um, okay, so that was quite a lot of information to take in. I know, but this course is designed to give you introduction into manufacturing process, right? So it's not really detailed. We don't go into too much detail on each of the operations. Just give you an introduction that so that you know that there are many machining operation that you can choose, and that's about cover the machining in this course. Well, if you're enrolling in a manufacturing course, machining might take a few, well, even like just milling or turning operation will take like a few lectures, like a few 3 hours lectures. But we just went over it really, really quickly, just to give you an introduction, to give you an idea of what type of operations you can do. Anyway, so next concept that we're going to look at is called machinability. Machinability is the ability of a material to be machined easily, right? So the machinability of metals is the ease with which the metals can be machined. So there are some criteria that we have to consider. For example, the surface finish and perfection of the machined metal, right? So if the surface after machining, if the surface is smooth and like really good, uh, a fine finish, then that material can be considered very good, has very high machinability, right? The tool life of the cutting tools used to cut metal. So a material with good machinability doesn't ruin the tool too much. So the tool doesn't get worn out too much for material with good machinability. But material with bad machinability, your tool will get worn down uh, much quicker. You have to replace the tool much more frequently, etc. Right? Cutting force and power required for machining the metal. Material with good machinability doesn't require much cutting force and power. Chip removal process. The chips should be easily broken into small pieces for easy handling. So remember, for cutting operation, right? So we are using a cutting tool to apply a shear deformation on the surface to produce a chip, and the chip needs to be removed from the surface quite easily. If you look at this picture, you can see that chips of metals are like flying away from the surface. But in this case, you can see the ships as well, but the ships are not actually like flying away from the surface, but you have like strips of ships, right? So you can say that this, but which case gives you better machine ability? You want like small ships that come away from the surface easily, or you want like large or long strips of metals on the surface. So for a material with good machine ability is a material that can form like small ships and um, to form small ships and like move away from the surface easier. Like in this picture here, when you have like ships flying away, instead of this picture here, when you have like strips of metals like clinging on to the workpiece and clinging on to the cutting tool, right? So material with good machine ability, the chip removal should be easily, the chip removal process should be easy. Right? The chip should be easily broken into small pieces so that it can be removed from the cutting surface easily. Okay. For steel, the machine ability of steel can be improved by alloying steel with lead and sulfur. Right? So if you add in enough lead and sulfur to the steel will become a grade called free machining steel. Right? So before adding lead and sulfur, the steel can have like long strips of chips, which we don't want, right? We don't want the long strip of chips, which can like entangle with the cutting tools, entangle with the work part. But when we add lead and sulfur in the molten steel and then cast it into the piece of steel, the chips are broken into small pieces and sort of like get away from the surface much easier. Okay, so so okay, if you want to design a component, a new component or a new machine, uh, you have to choose a material for that machine, right? For that component, right? And then you have to choose the manufacturing process for that component. So if your chosen manufacturing process is machining, like milling or lathe, turning, etc., you have to choose the material accordingly, right? So you have to choose if your chosen manufacturing process is machining, you might have to choose like free machining steel, so steel with added lead and sulfur. But if you choose other type of steel, it will be more difficult to produce the workpiece, right? Or the other way around. Or the other way around, for example, if you are producing a component and then you're choosing a material for that component, then you have to choose the manufacturing process that is appropriate for that material. Okay, and you have to think about all the economics of producing that component, like what is the cost per unit for that component, so that you choose the correct manufacturing process. And it depends on how many pieces you want to produce, and etc. Right? Okay, so cutting tool failure. The cutting tool can fail, right? There are um, there are three modes that the cutting tool can fail, like fracture failure, temperature failure, and gradual wear. Fracture failure is when the fracture failure is the mode of failure that occurs when the cutting force at the tool point becomes excessive. So you have too much cutting force on on the tool point, and it causes the cutting tool to fail in a brittle fracture. Right? So that's fracture failure. And temperature failure is when the cutting temperature is too high for the tool material, causing the material at the tool point to soften. And, and because when the cutting tool is softened, that means you can get plastic deformation easier. So the cutting bits are plastically deformed, and when the cutting bits are plastically deformed, you have a loss of the loss of sharpness, right? So this is or you have a loss of sharpness. So this is called temperature failure, right? When the temperature is too high, and and um, and what happens when temperature is too high is you have a loss of strength, a loss of hardness, right? So like in this graph here, you can see that, for example, to high-speed steel, it's got good strength, but it doesn't have good hardness or and wear resistance, right? So if you're using high-speed steel at high temperature, what happens is that it will lose its strength and hardness, and it becomes softer at higher temperature, and it will be plastically deformed. So you will lose the cutting edge because the cutting edge is plastically deformed. Okay, so you have a premature loss of the cutting tool. Right? Um, a gradual wear, which is okay. So the fracture failure and the temperature failure is premature loss of cutting tool. The gradual wear is preferable because it is longer time, right? It takes longer time because we know that the tool will wear eventually, and if it has a gradual wear, right? So the gradual wearing of the cutting edge uh, over time, because you keep using it, you are losing a little bit of the cutting edge, and because of the wearing of the cutting edge causes the loss of the tool shape and causes the reduction in cutting efficiency, uh, and you have and then you start to get more and more wear because the tools becomes heavily worn, and finally the tool will fail, similar to the temperature failure, right? So you have plastic deformation, blah blah blah, right? Okay, so cutting tool and tool material, like I've briefly mentioned about this before. The cutting tool must be the cutting tools and the cutting tool material must be harder than the cut workpiece. Okay, and it should have good toughness. I'm sorry, should have good toughness to avoid fracture failure. It should have hot hardness to retain hardness at high temperature to avoid temperature failure. It should have good wear resistance to resist abrasive wear, so you can have longer life cutting tool, and it should be chemically stable, right? So it shouldn't react to coolants or lubricants, etc. Okay, so uh, the tool material are crucial component in machining process. The choice of the tool material depending on the workpiece material, machining process, cutting condition, and desired results. Common tool materials are high-speed steel and carbide or cemented carbide inserts. So this is the like normal shape for the high-speed steel, uh, and we have a solid tool, right? So the whole piece is made from high-speed steel. The high-speed steel is a versatile and widely used tool material. It has alloying elements like tungsten, molybdenum, chromium, and vanadium. So these alloying elements are added in there to increase hardness and increase wear resistance at especially at high temperature. and the high-speed steel are suitable for a wide range of machining operation, like for material like carbon steel, alloy steel, and non-ferrous metal. For carbide insert or cemented carbide, uh, this it looks something like this, right? So you have the shank that is made from tool steel, and you have the seats or the shim, right? And then you put in your carbine bits, right? The yellow bits are the cutting bits that is made from the carbide, right? The yellow bit is called insert because you insert it, and you insert it into the seats, and you have mechanical clamp to clamp it in place, right? The carbide or cemented carbide inserts are tools that are made from hard carbide particles like tungsten carbide. Usually, you have tungsten carbide particles that are binded together uh, using uh, using other material like cobalt, right? So it is a metal matrix composite. It is a composite with the metal as the matrix, and you have the carbide particle as the reinforcement. But in this case, we are using the reinforcement as the main material, not the matrix. Usually in composite material, the matrix is the main material, and we add in the reinforcement to improve the property of the matrix, right? But for cemented carbide, the main property that we want is the property of the carbide particles, and the matrix. In this case, we use cobalt, which is a metal. We use cobalt as a binder, as a glue to bind all the cemented carbide, to bind the carbide particles together. These type of material are extremely hard, so they are very wear resistant. They are ideal for machining hard and abrasive material like stainless steel, cast iron, high temperature alloys, etc. Right? And the carbide tools usually maintain their hardness at high temperature really well compared to high speed steel. Right? So it can use to cut material at high speed. Right? So high cutting speed usually produces high temperature, but because the carbide cutting tool can withstand high temperature really well, you can use it at high cutting speed. Compared to high speed steel, when at higher temperature, it becomes softer. So you don't want to use high speed steel at high cutting speed because you will heat it up and it will get softer and you will get premature failure. Okay, so this is the list of material that I showed you earlier. You can see that high-speed steel has got good strength and toughness, but not very good hot hardness and wear resistance. And the carbide particle has better property in terms of hot hardness and wear resistance compared to high-speed steel. Even though it doesn't have the same strength as the steel, it's more brittle as well. So it hasn't got the same toughness as the high speed steel, but it's got much better hot hardness and wear resistance. And if you want to machine even harder material, you have to choose like um, um, harder material on here as well, like cermets or diamond coated bits or aluminum oxide bits, etc. Okay, so the parameters related to machining, right? So uh, we can separate it into two part, right? So this is sort of a recap. So the work part, you have the work part material and also the geometry of the work part. You can have rotational and non-rotational. Right? And for the cutting tool, you the cutting tool the characteristic property of the cutting tool is that you need good toughness, you need hot hardness or red hardness, you need good wear resistance, chemically stable, right? So usually we choose tool steels like high-speed steel and also carbide insert. Okay. Um, right. So for the work, the diameter related to the work part, like the material, we look at the machinability of the material. The machinability denotes the relative ease with which the material, usually metal, can be machined using appropriate tooling and cutting condition. So how easy it is to remove excess material without damaging the tool, etc. Right? The criteria to evaluate machinability is the tool life, the forces and power used to machine that metal, the surface finish afterwards, and the ease of chip disposal. So these are the criteria for machinability. And we usually add in lead and sulfur in the steel to uh, to make it more machinable.